Where are you right now? Not just your coordinates on a map or the name of a city, but here, in this very moment. What time is it in your corner of the world? Is it dark outside, the kind of darkness that wraps the windows like a blanket, or is the sun still spilling across the sky, stretching the day just a little longer? Maybe you're in bed, phone balanced in your hand, your head sinking into the pillow. Or maybe you're curled up on a couch, letting the day unravel behind you while the hum of the world softens. Wherever you are, I want you to imagine something you've never really stopped to question. You reach out and touch the table beside you. It feels solid, firm, dependable. The floor beneath you is holding you up. Your hands, your arms, they're yours, sturdy, physical, real. It's comforting to believe the world is exactly as it appears, made of matter, solid through and through. But what if that solidity was a trick? What if, beneath everything you see, touch, and know, there was almost nothing at all? Not nothing like empty air, but nothing like a silence so complete it feels like the pause before the first note of a song. Atoms, the building blocks of you, me, this entire room, are 99.9999999% empty space. And yet here we are feeling solid, real, undeniable. It doesn't seem possible, does it? And yet it's true. We've built our lives, our history, our sense of self on a foundation we can't actually see. A foundation that, if you could zoom in far enough, would dissolve into something so strange, so alien, you might not even call it stuff anymore. Before we untangle that mystery, before we step into the impossible truth of what you are, we have to go back, way back, to the time when we thought we understood the world and all of it fit neatly into a picture so simple, so certain, it was almost childlike. We like certainty. We like to know that the ground beneath our feet will not suddenly give way, that the objects in our lives will stay where we left them, that our own bodies will keep their shape when we wake up in the morning. Matter, the stuff of the universe, has always been our anchor. It is the foundation of every structure we've built, the canvas for every story we've told, the unshakable reality against which we measure every change. When we think about matter, we imagine something tangible, something you could hold in your hands if only you could zoom in small enough. We picture it like the pieces of a Lego set, tiny, solid building blocks that snap together to form something bigger. The chair you sit on, the food you eat, the pen you hold, these are just arrangements of those building blocks. The world is a giant construction set, and the pieces are physical, indivisible, and permanent. School reinforced this picture. You might remember learning about atoms in science class, little solar systems of electrons whizzing around a nucleus of protons and neutrons. The diagrams were colorful and neat, their proportions carefully drawn, their components labeled like a family tree. The message was simple: this is what everything is made of. These are your bricks. And because we trust what we can see, especially when it comes from textbooks, teachers, and diagrams, we accepted it. The atom was the smallest thing in the universe, solid at its core, indestructible in its nature, a kind of eternal marble from which the universe was carved. If you could take anything in the world, break it apart and break it again and again and again, you would eventually find this tiniest, solid bead that could not be broken further. That mental image gave us comfort. It gave the world a kind of tidy order. Even if everything else was chaotic, politics, relationships, the weather, matter was matter, the bricks were still in place. We rarely stopped to think about how little we had truly seen of these bricks. The smallest thing most of us ever physically encounter is a grain of sand or a dust mote drifting through sunlight. An atom is so much smaller than that dust mote that it's almost impossible to visualize. In fact, if an atom were the size of a football stadium, the nucleus at its center would be the size of a marble, and the electrons would be specks of dust whirling somewhere in the stands. The rest, empty. But our minds don't like empty. Empty feels like nothing, and nothing is unsettling. So we fill it in with certainty. The atom is a solid thing. That certainty becomes invisible to us, like the air we breathe. And yet there were cracks in this assumption, even before science had the tools to prove it wrong. Philosophers in ancient Greece, like Democritus, imagined atoms not as miniature pebbles, but as invisible, uncuttable units, whose shapes and arrangements gave rise to all things. His view was poetic but speculative, and no one could prove or disprove it. For thousands of years, the nature of matter remained a mystery shrouded in guesswork. The Industrial Revolution changed that. As chemistry matured and tools improved, we began to see the behavior of atoms indirectly. We noticed how substances reacted in precise, repeatable ways, how gases filled containers, how metals combined, how heat transformed solids into liquids. The pieces of the puzzle seemed to fit the Lego analogy well enough. But here's the first strange contradiction. If matter is so solid, why does it behave like something that can be compressed, stretched, and dissolved? If its building blocks are rigid, why can they flow like water or disappear into vapor? We brushed aside those questions, saying it was all just the arrangement of the bricks, nothing more. Then came electricity. In the late 19th century, experiments with cathode rays, streams of mysterious particles, showed that atoms could eject smaller bits. This was like tapping your Lego brick and watching a tiny splinter fly off. Solid and indivisible? Apparently not. The atom was not the ultimate bead, but a container of even smaller things. Still, the image persisted in popular imagination. Even after scientists discovered electrons, protons, and neutrons, the solid little solar system remained our mental model. It was neat, it was easy to picture, and it gave us the same comfort as believing the Earth is flat when you've never left your hometown. Why imagine something stranger when the simple picture works well enough? But cracks don't close themselves. The more scientists looked, the stranger matter became. It wasn't just that atoms were mostly empty space, it was that the particles themselves didn't behave like little marbles at all. They acted like something else. Sometimes like particles, sometimes like waves, sometimes like both, depending on how you looked at them. It's here that our everyday assumption begins to falter entirely. The solidity we feel when we press our hands together isn't the result of particles physically touching. In fact, they never do. What you're feeling is the electromagnetic force, the invisible pushback, as the electric fields of your hand's atoms repel the electric fields of the object you're touching. You're not touching in the way you think. You're hovering just above, endlessly separated by space, held apart by invisible tension. This is where the first unsettling question creeps in. If the building blocks of matter are mostly nothing, and if their contact is just invisible fields repelling each other, what exactly is the solid world we trust so much? The answer requires us to step back in time again, to the era when our scientific picture of reality was still young, before we had microscopes that could peer into the atom, before quantum physics could unravel its secrets. Back then, we believed in a clockwork universe, a reality that could be measured, predicted, and controlled like the gears of a well-made machine. Newton's laws of motion ruled the cosmos. They told us that every object had a place, a speed, a direction, and a future that could be calculated exactly. Matter, under this view, was a passive player, shaped and moved by forces, but fundamentally simple. Drop an apple and it falls. Push a cart and it rolls. The rules were clear, clean, and absolute. This classical picture was intoxicating. It suggested that if we could just gather enough data, measure every particle's position and motion, we could predict the entire future of the universe. It was a vision of total control, and it made matters seem tame. But that vision, as comforting as it was, carried within it the seeds of its own unraveling, because as our instruments improved, we began to notice that matter didn't always play by the rules. Light bent in ways we didn't expect. Heat moved in strange patterns. Substances behaved differently at different scales. And when we tried to explain these anomalies, the neat, solid picture of matter began to dissolve. The closer we looked, the more the bricks seemed to crumble into something we couldn't quite name. The atoms that once felt like bedrock now looked like vast, mostly empty arenas where tiny sparks of energy danced and flickered in patterns that defied intuition. The universe we thought we understood was shifting under our feet, and we were only just beginning to sense how deep the shift would go. Once upon a time, though not so long ago in the grand sweep of history, we thought we had it all figured out. The world seemed solid, predictable, and above all, understandable. We had stepped out of the medieval haze of superstition and into the age of reason, and with the tools of observation and mathematics, reality was finally yielding its secrets. The story we told ourselves about matter was elegant and convincing. It was stuff, made of smaller stuff, moved by forces, all of it arranged in a vast, perfect machine. If you lived in the era of Isaac Newton, you would have felt like the universe had finally become transparent. Newton's Principia Mathematica, published in 1687, was a kind of gospel for the scientifically minded, a text that explained the motions of planets, the fall of apples, the swing of pendulums, the rise and fall of tides. His laws of motion and universal gravitation didn't just describe these phenomena, they united them under the same principles. Whether it was a moon orbiting a planet or a pebble rolling down a hill, the same rules applied. In this clockwork universe, matter was made up of particles, infinitesimally small, perfectly solid, and fundamentally inert. These particles had mass, and their motion was determined by forces acting upon them. If you knew where every particle was and how fast it was moving, you could, in principle, predict the entire future of the universe. The metaphor was intoxicating, the cosmos as a giant watch, wound up at the beginning of time, ticking along with flawless precision. In Newton's world, there was no room for uncertainty. Cause led to effect with mechanical certainty. Push an object with a certain force, and it would accelerate in a predictable way. The idea of randomness or fuzziness at the foundation of reality would have seemed absurd, even laughable. To scientists of the Enlightenment, such ideas belonged to mystics, not to serious thinkers. And yet this certainty depended on something subtle, an assumption we rarely think about, that space and time themselves were like a smooth, invisible stage on which the particles danced. This stage was absolute and unchanging. Distances were distances, seconds were seconds, no matter where you were or how you moved. It was the universal backdrop, and matter was the performance upon it. The early chemists, inspired by Newton's precision, set about identifying the elements, pure substances that could not be broken down further. By the late 18th and early 19th centuries, scientists like Antoine Lavoisier and John Dalton were giving us a periodic order to the chaos. Dalton, in particular, formalized the atomic theory, that all matter was composed of indivisible atoms, identical within each element, and combining in fixed ratios to form compounds. This was the Lego brick model of reality, now given mathematical backbone. Dalton's atoms were not yet the colorful, whirling spheres you saw in school textbooks. They were abstract points of mass, invisible but logically necessary. You couldn't see them, but you could infer their existence from the way substances behaved. Matter, in this picture, was simple, uniform, and permanent. For a century, this worldview grew more sophisticated, but remained essentially the same. James Clerk Maxwell, in the mid-19th century, gave us the equations of electromagnetism, showing that electricity and magnetism were not separate phenomena, but aspects of the same underlying field. His work hinted that the universe was even more unified than Newton had imagined. Matter was still solid and knowable, but now it interacted through fields, smooth, invisible influences that could reach across empty space. By the late 1800s, it seemed that science had uncovered almost everything important. Lord Kelvin famously declared that physics was essentially complete, with only a few small clouds on the horizon. The two clouds he referred to were anomalies, tiny discrepancies in experimental results that didn't quite fit the existing theories. Few imagined that those clouds would explode into storms that would remake the entire picture of reality. One of those clouds was the nature of light. For centuries, scientists had debated whether light was a particle or a wave. Newton himself leaned toward particles, while others, like Christian Huygens, argued for waves. By the 19th century, the wave theory seemed to have won. Experiments showed that light could interfere with itself, creating patterns just like ripples in water. This wave behavior fit beautifully with Maxwell's equations, which described light as an oscillation of electric and magnetic fields moving through space. But if light was a wave, what was waving? For sound waves, the answer is clear: air molecules. For water waves, it's water. So what medium carried light? Scientists postulated the luminiferous ether, an invisible, weightless substance that filled all of space and served as the medium for light waves. The ether was undetectable, but it was assumed to be real, because in the Newtonian mindset, waves had to have something to wave in. The trouble began in 1887 when Albert Michelson and Edward Morley conducted an experiment to detect the Earth's motion through this ether. According to theory, the speed of light should change depending on whether you were moving with or against the ether's flow. But no matter how they measured it, the speed of light came out the same. The ether was nowhere to be found. This was unsettling, but it didn't yet shatter the worldview. Scientists assumed they figure it out eventually. They still trusted the basic picture: particles, forces, fields, and an absolute backdrop of space and time. The real earthquake began in the early 20th century. In 1905, a young patent clerk named Albert Einstein published a series of papers that would reshape physics. One of them, the special theory of relativity, explained the Michelson-Morley result by discarding the ether entirely. In Einstein's universe, the speed of light was constant for all observers, no matter how they moved, and this meant that space and time themselves were not fixed stages, but flexible, relative quantities. Relativity was a shock, but it still preserved much of the Newtonian spirit. Matter remained matter, particles remained particles. The real trouble for solidity would come from a different direction entirely, one that started not with grand cosmic theories, but with tiny, stubborn problems in understanding atoms. At the dawn of the 20th century, experiments in atomic physics were piling up oddities. Ernest Rutherford's famous gold foil experiment in 1909 revealed that atoms were mostly empty space, with a dense nucleus at the center. This was surprising enough, but more puzzling still was the behavior of electrons. According to classical physics, electrons orbiting a nucleus should constantly radiate energy and spiral inward, collapsing the atom in a fraction of a second. Obviously, that wasn't happening. Atoms were stable. Something was missing from the picture. Enter quantum theory. Max Planck, trying to explain the spectrum of light emitted by hot objects, proposed in 1900 that energy came in discrete packets or quanta rather than being continuous. This was a mathematical trick at first, but it worked. In 1905, Einstein took the idea further, showing that light itself behaved like particles, later called photons, in certain experiments. The neat categories of wave and particle were starting to blur. As the years went on, Niels Bohr, Werner Heisenberg, Erwin Schrödinger, and others built a new framework for understanding the atom. Electrons didn't orbit like planets. They existed in fuzzy clouds of probability, their positions and momenta never exactly knowable at the same time. The solidity of matter, it turned out, was an emergent illusion, arising from the interactions of these probabilistic clouds and the electromagnetic fields between them. The Newtonian dream of a clockwork universe was over. In its place stood something stranger, a universe where matter could be wave and particle at once, where observation itself influenced outcomes, where the very building blocks of reality were not solid but ephemeral patterns in a shifting field. And yet, despite all this strangeness, our daily experience still told us the old story. We still sat on chairs, held cups, walked on sidewalks. The world felt solid. The Newtonian picture might be dead in physics, but it lived on in our senses, our instincts, and our language. It's hard to shake off centuries of mental habit. But the deeper you go into quantum mechanics, the harder it is to believe in that old solidity at all. At the smallest scales, particles are not little marbles. They are excitations in fields, flickering in and out of existence, connected in ways that defy classical logic. And that, perhaps, is the most unsettling truth of all. The solid world we cling to is not made of solid things. It is made of relationships, interactions, and probabilities. The story we once told about matter, clear, mechanical, and certain, has become a ghost story. Not a horror story, but one of haunting beauty, where the familiar dissolves into the mysterious, and the ground beneath your feet turns out to be mostly nothing at all. Even knowing the quantum story, you still feel the table under your hand. You can press your palm into it, knock on it, even stub your toe on it if you're unlucky, and your nervous system will send you an immediate and painfully persuasive reminder that it's real. Your body does not care that atoms are 99.9999999% empty space, or that the electrons in your hand never truly touch the electrons in the wood. To your senses, solidity is not a theory. It is a fact written in pressure, vibration, and nerve endings. This is because your brain is not built to perceive reality as it is. It's built to perceive reality in a way that is useful. Your senses are not open windows onto the world. They're more like carefully edited films, showing you just enough of the right scenes to keep you alive and functional. Anything else is cut, blurred, or replaced with a convincing illusion. Take vision, for example. Your eyes capture light bouncing off surfaces, but they don't deliver a perfect photograph to your mind. They send electrical signals, which your brain then interprets, cleans up, and stitches together into a stable image. The blind spot in each eye is simply filled in with whatever your brain assumes should be there. Your perception of solid color is a construct. Reality, at the smallest scale, has no color at all. Touch is no different. When you rest your hand on a table, the atoms in your skin don't pass through the atoms in the wood because electromagnetic forces between them repel one another. What you feel as firmness is actually a constant, invisible standoff, an electromagnetic barrier dressed up by your brain as hardness. That sensation is not a direct experience of matter itself. It's a translation, a metaphor your nervous system uses because you can't directly feel the quantum field. And this translation is biased towards survival, not truth. If the brain had evolved to perceive empty space between atoms or to visualize probability waves, we might not have made it far as a species. Imagine trying to walk across a room while seeing everything as ghostly flickers of energy, endlessly vibrating in a void. You'd trip, stumble, and starve before dinner. Instead, evolution gave us a coherent, simplified, and let's be honest, mostly false picture of the world. This is why the old Newtonian model remains so persuasive, even if it's wrong at the deepest level. Our biology conspires with our habits of thought to keep the illusion alive. We don't just see the world as solid, we feel it, hear it, and move through it as if solidity were the most basic truth. But this sensory editing can be fooled. Optical illusions exploit the shortcuts your brain takes, revealing just how much of what you see is an assumption. The famous Muller illusion, where two lines of equal length appear different because of the arrows drawn at their ends, works because your brain is applying unconscious rules about depth and perspective. Magic tricks exploit these same shortcuts in the tactile and auditory domains. The magician doesn't make the coin disappear. Your attention, guided by your brain's expectations, simply edits it out of your conscious story. On a deeper level, your brain's model of the world is more of a prediction machine than a recording device. Neuroscientists call this predictive processing. Your senses provide raw data, but your brain constantly compares that input against an internal model of reality. Most of what you perceive is your brain's best guess about what's out there, updated just enough by sensory evidence to avoid deadly mistakes. In this way, the illusion of solidity isn't just a passive misinterpretation, it's an active creation. You are literally generating a stable, touchable world from a haze of probabilities. The feel of a chair under you is as much a construction of your nervous system as the color blue or the sound of your name. And this brings us to an unsettling but fascinating point. If perception is an active process, then reality, as far as you experience it, is partly made in your head. That doesn't mean the universe is imaginary. It means that the specific way you encounter it is tailored, simplified, and shaped by the limitations of your sensory system and the needs of your survival. This is also why we tend to underestimate how weird the microscopic world is. We rarely, if ever, encounter it directly. Our senses are tuned for the middle scale, the world of meters, seconds, and kilograms, not the scale of femtometers, nanoseconds, and electron volts. At those smaller scales, the familiar rules dissolve. Objects behave like waves, positions blur into probabilities, and the very notion of thingness starts to feel meaningless. But your brain filters all of that out, handing you a crisp, reliable version of reality that you can navigate without existential panic. Yet every now and then, cracks appear in the illusion. We see it in moments of déjà vu, when reality feels slightly off, or in strange perceptual experiences like the rubber hand illusion, where a fake hand can be made to feel like your own. These glitches reveal the scaffolding of your perception, the fact that solid reality is built from signals and assumptions, not from direct contact with objective truth. Think about music. When you listen to a song, you don't hear the raw vibrations of air molecules. You hear rhythm, melody, and emotion. Your brain transforms mechanical waves into a structured experience that can make you cry, dance, or remember someone you once loved. That transformation is not in the sound, it's in you. The same is true for solidity. The desk, the cup, the bed frame, all of them are patterns of interaction dressed up by your nervous system as solid matter. This is why physics can say, with complete seriousness, that atoms are mostly empty space, and yet you can still spill coffee on yourself. The two truths aren't contradictory, they're just truths at different levels of description. One is the deep, microscopic truth of quantum fields and probabilistic particles. The other is the useful, survival-friendly truth of human perception. And here's the twist. Once you start thinking about reality this way, it's hard to stop. You begin to notice the seams in the story your senses tell you. You wonder how much of your daily experience is a kind of hallucination, a shared, species-wide hallucination that we've agreed to call real. Your brain, in this view, is not simply observing the universe. It's participating in its creation, at least in the sense of creating the version you live in. That version is full of objects, edges, colors, and textures, but those are all translations of something far stranger. And when you realize this, the question naturally arises. If your brain is already filtering and simplifying the truth, what happens when you zoom past the human scale entirely? What happens when you leave behind the middle world of doors and cups and clouds and plunge into the realm where atoms themselves dissolve into something indescribable? That is where the tiny and the weird begin. And the moment you take that leap, the last vestiges of the solid, dependable world you thought you knew will melt away. Close your eyes for a moment and imagine shrinking, not the casual, poetic kind of shrinking, but the impossible kind. Imagine yourself getting smaller than a grain of sand, smaller than a dust mote, smaller than a single cell in your body. Shrink until you are standing on the surface of an atom, or rather hovering above it, because there is no surface in the way you expect. You are in a strange, vast emptiness, and far below you is a tiny, bright point, the nucleus. At this scale, your sense of proportion starts to shatter. The nucleus is so small compared to the whole atom that if the atom were the size of a football stadium, the nucleus would be a marble placed at the center. The electrons, those elusive, negatively charged particles, aren't like little planets whizzing neatly in orbits. They are smears of probability, clouds of potential location that spread across the stadium in strange, fuzzy shapes. You can never point to one and say, "There it is," without uncertainty. The space between the nucleus and the electron cloud is vast, not empty in the casual sense, but empty in the sense of no physical particles at all, only fields, forces, and the possibility of interaction. Most of the matter in matter is this kind of nothing. Here the rules are not the ones you know. A particle can behave like a wave, not metaphorically, but literally, spreading out over space and interfering with itself like ripples on a pond. The famous double-slit experiment shows this in action. Fire individual electrons at a barrier with two slits, and they'll create an interference pattern on the other side, as if each one was somehow passing through both slits at once. But when you measure which slit they go through, the interference vanishes and the electrons behave like tiny bullets. Observation itself changes the outcome. At this scale, certainty becomes impossible. Werner Heisenberg's uncertainty principle tells us that you can't know both the position and momentum of a particle at the same time. The more precisely you pin down where it is, the less you know about how it's moving, and vice versa. The universe is built not from perfectly located marbles, but from clouds of possibility that only solidify into specifics when something interacts with them. And these particles, electrons, protons, neutrons, are not even the most fundamental players. Zoom in further, and you find they are made of quarks, bound together by gluons in an intricate dance governed by the strong nuclear force. The gluons don't just stick things together, they constantly exchange energy, creating a restless, boiling interior. Even the vacuum, the so-called emptiness of space, is not truly empty. Quantum field theory tells us it teems with activity, virtual particles popping in and out of existence, fleeting fluctuations in energy that never quite vanish. It's a world of restless impermanence. What we call matter is really the visible tip of an invisible web of fields, the electron field, the quark field, the photon field, each stretching across the universe, each able to produce particles when energized. The particles are not little nuggets of stuff. They are excitations, like ripples on a vast, invisible ocean. When the ripple subsides, the particle is gone, but the field remains, ready to be stirred again. If this already sounds strange, it gets stranger still. In quantum mechanics, Entanglement binds particles together in ways that defy our classical understanding. Two particles that have interacted can remain connected, such that measuring one instantly determines the state of the other, even if they are light years apart. Einstein called this spooky action at a distance, because it seemed to violate the cosmic speed limit set by relativity, yet experiments have confirmed it again and again. The universe, at its smallest scale, appears to have ways of keeping secrets, or perhaps of sharing them instantly, that no local, mechanical model can explain. In this realm, objects are not isolated. They are probabilities woven into a network of interactions. The chair you sit on, the hand you place upon it, are made of atoms whose electrons are in constant quantum conversation, pushing and pulling with invisible forces. The hardness you feel is a collective effect, the result of countless repulsive interactions between the electric fields of your atoms and the chair's atoms. Without those fields, without the dance of quantum charges, you would fall right through it. Temperature, too, becomes a quantum story. Heat is not a substance, but the motion of particles, vibrations rippling through the lattice of atoms that make up a solid. At the quantum level, these vibrations come in discrete packets called phonons. Cold is not the absence of heat, but the slowing of this motion, the settling of particles into low energy states. At absolute zero, motion doesn't completely stop. Quantum mechanics forbids it. Even in the coldest possible place, there is a faint hum of activity, a reminder that the vacuum itself is never truly still. This tiny, weird world is also where chemistry is born. The shapes of electron clouds, determined by the strange mathematics of quantum mechanics, dictate how atoms bond into molecules. The softness of butter, the fragrance of a rose, the way salt dissolves in water, all of it emerges from the probabilistic patterns of these electron clouds. The everyday properties we rely on are quantum miracles in disguise. And yet, as alien as this realm is, it is also breathtakingly beautiful. Imagine watching an atom fluoresce, emitting a photon as an electron drops to a lower energy level. That photon, a tiny quantum of light, might travel across the universe without scattering, carrying its silent message until it meets another atom and is absorbed. Imagine a particle existing in a superposition, in multiple states at once, until the moment you measure it. Imagine that measurement not as a cold, mechanical act, but as a kind of cosmic conversation, a question asked, an answer given, and the universe reshaped in the asking. In the tiny and the weird, nothing is truly separate, and nothing is completely certain. The solidity of the macroscopic world is built on a foundation of constant change, restless interaction, and inherent ambiguity. It's not that matter isn't real, it's that reality at this level refuses to conform to our everyday definitions. And when you start to think about this too long, your mind naturally begins to wander to the opposite extreme. If things become stranger and less tangible the smaller we go, what happens when we go the other way? When we scale upward, beyond the atoms and the cells and the mountains, into the star systems and the galaxies, does the weirdness fade, replaced by the clean clockwork of Newton's skis, or does it get stranger still? Because the truth is, the cosmos is not made of neat, predictable wheels turning in the void. At the largest scales, patterns emerge that are just as astonishing and just as humbling as the dance of quarks and electrons. The tiny and the weird may live in the atom, but the vast and the cosmic have their own secrets, and those secrets may reveal that the strangeness of the quantum world never really goes away. Imagine reversing the shrinking we did before. Instead of diving deeper into the atom, you begin to expand. The nucleus falls away beneath you, the electrons blur into clouds, the stadium becomes the entire city, then the continent, then the whole blue-green sphere of Earth. You keep going. The moon slips past like a silver coin. The sun, once so impossibly huge, shrinks to a brilliant bead. Beyond it, the solar system unfurls, a grand clock of planets and icy remnants, all dancing around a center that is, itself, moving through the galaxy. From this vantage point, you might expect the world to make more sense again. After all, Newton's laws first came alive by describing the motions of the planets. Space seems like the perfect place for the old, comforting image of a clockwork universe. Stars wheeling in the dark, each path predictable, each movement dictated by gravity's steady hand. And yes, at first glance, the heavens look tidy. The planets follow elliptical orbits, comets return with patient regularity, and distant suns circle their partners in graceful binaries. These patterns are real, and they can be predicted with incredible accuracy. But the deeper we peer into the vastness, the more that tidy picture frays. First, there's scale. The Earth orbits the Sun at a comfortable 93 million miles, but the Sun itself is just one star among roughly 100 billion in the Milky Way galaxy. Our galaxy is a spiral island of stars, gas, and dark matter about 100,000 light-years across, a span so large that a beam of light, traveling at 186,000 miles per second, would take 100,000 years to cross it. And yet, the Milky Way is just one of perhaps 2 trillion galaxies in the observable universe. Distances like these are not just hard to imagine, they break the way we normally think about place and time. If you could somehow watch the Andromeda galaxy right now, you'd be seeing it as it was more than 2 million years ago, because that's how long its light has taken to reach you. In the vast and the cosmic, looking is always looking back in time. The farther you look, the older the universe you see. And when we look deep enough, we see something extraordinary, the cosmic web. Galaxies are not scattered randomly through space. They form vast filaments and clusters, like threads in an invisible tapestry stretching across the universe. Between these threads lie enormous voids, empty regions millions of light-years wide, where almost no galaxies reside. Matter itself is shaped into a structure on a scale so huge that even our largest simulations struggle to contain it. This grand pattern, it turns out, is the result of the same laws that govern the tiny. The way galaxies clump and form is influenced by quantum fluctuations from the earliest moments of the universe, ripples in the infant cosmos, stretched to cosmic size by inflation. The seeds of this vast structure were planted in a time so early and strange that our physics still can't fully describe it. And then there's the matter problem, or rather, the dark matter problem. When astronomers measured how galaxies rotate, they found something puzzling. Stars at the edges move far faster than they should, given the visible mass. The only explanation that fits is that galaxies are embedded in massive halos of invisible matter, matter that doesn't emit or absorb light, that interacts with regular matter only through gravity. We call it dark matter, and it makes up about 85% of the matter in the universe. Despite decades of searching, we still don't know what it is. Dark matter isn't the only invisible player. There's also dark energy, an even stranger phenomenon. In the late 1990s, astronomers discovered that the universe's expansion is accelerating, as if some mysterious force were pushing galaxies apart. Dark energy is our placeholder name for this effect, and it accounts for about 70% of the total energy in the cosmos. That means that everything we've ever seen, every star, planet, cloud, and creature, makes up less than 5% of the universe. In other words, most of reality is dark, not dark as in evil, but dark as in unknown, and yet it shapes the fate of everything. The vastness doesn't just dwarf us in space, it also challenges us in time. The universe is 13.8 billion years old, but it will not remain as it is forever. Stars will burn out, galaxies will drift apart, and in the far future, the cosmos may become cold and dark, a heat death where entropy is maximized and no new complexity can arise. Or perhaps it will collapse back in on itself in a big crunch, or tear itself apart in a big rip. The fate of everything is still an open question, and it depends on the nature of the dark forces we barely understand. And yet, for all this immensity and uncertainty, there are connections between the vast and the tiny that are almost poetic. The same quantum mechanics that governs the dance of electrons in an atom also governs the behavior of particles in the early universe. The same physics that explains why atoms are mostly empty space also explains why galaxy clusters are mostly empty space. The same interplay of forces that holds your body together also binds stars into spirals and galaxies into clusters. Gravity, the weakest of the 4 fundamental forces, shapes the largest structures of all. It pulls matter into stars, and stars into galaxies, and galaxies into clusters. Electromagnetism, so much stronger, shapes the chemistry of life and the light of the stars. The strong and weak nuclear forces work invisibly in atomic hearts, forging the elements that will someday drift in space until they become part of planets, oceans, and living beings. Even the light that reaches your eyes on a clear night is a kind of ancient whisper. The photons from distant stars began their journey long before you were born, before your species even existed. Some left their stars when the Earth was still molten rock, others when dinosaurs walked the continents. In a very real sense, stargazing is time travel. And if the cosmic scale seems too immense to grasp, consider this. Your body contains atoms forged in stars that died billions of years ago. The iron in your blood, the calcium in your bones, the oxygen you breathe, all of it was born in stellar furnaces and supernova explosions. The vast is not just out there, it is in you. This is perhaps the most humbling revelation of all. The tiny and the vast are not separate realms. They are different faces of the same reality, connected in ways we are only beginning to understand. And somewhere in between those extremes, in the middle-sized world where human lives unfold, we experience a version of that reality shaped by our senses, our culture, and our imagination. But what if even this version, the one that feels most real to us, is not quite what it seems? What if the entire thing, from quarks to galaxies, is less like a physical stage and more like a simulation? Because once you accept that most of the universe is invisible, that solidity is an illusion, and that observation itself changes outcomes, the leap to simulation isn't so far. What if reality isn't a thing at all, but a kind of rendering, one that springs into being only when needed, only where there's an observer to witness it? What if the universe isn't a stage made of matter at all, but a kind of story, one that only exists when someone is reading it? What if the atoms, the galaxies, the warm coffee cup in your hands are more like characters in a play than bricks in a wall? It sounds like philosophy, maybe even science fiction, but the more we learn about the nature of reality, the less outrageous it becomes to ask. Consider the strange way the quantum world behaves under observation. In the double-slit experiment, particles act like waves when no one's watching, but collapse into definite points when measured. It's as if the universe waits to see what we want before deciding what to be. This isn't to say that consciousness creates reality in the mystical sense people sometimes imagine, but it does hint that reality might not be fully out there until an interaction, an observation, brings it into being. From here, the simulation idea starts to feel uncomfortably plausible. If you've ever played a video game, you know the world isn't rendered in full detail all the time. Only the parts you can see, hear, or interact with are actively simulated. The rest remains a set of instructions, waiting to be called upon. Could our universe work the same way? Could the particles and fields and galaxies be the rendered output of some deeper, hidden code? The physicist John Wheeler once summed this up in 3 words: it from bit. The it, the physical stuff of the world, emerges from bit, the information that underlies it. In this view, reality isn't fundamentally made of matter or energy, but of information. Particles are just expressions of data. Forces are rules of computation. Space-time itself is the program's coordinate grid. Philosophy, of course, got here long before physics did. In the 17th century, the philosopher George Berkeley argued that to be is to be perceived, that objects exist only in the mind of an observer. For Berkeley, the ultimate observer was God, whose perception sustains the world at all times. Modern versions of the idea replace God with some other kind of ultimate processor, maybe an alien supercomputer, maybe a deeper layer of reality beyond our own. Then there's the brain in a vat thought experiment. Imagine that you are nothing more than a brain floating in a tank fed electrical impulses by some advanced machine. Everything you see, hear, and feel is the result of this artificial input. From the inside, it would be indistinguishable from real life. The twist is, there's no way to prove you aren't such a brain. Every piece of evidence you might gather could itself be part of the simulation. Simulation theory, popularized by philosopher Nick Bostrom, pushes this further. If civilizations eventually develop the ability to run hyperrealistic simulations of conscious beings, then the number of simulated beings could vastly outnumber the number of real ones. Statistically, it might be more likely that you are inside a simulation than outside of one. That's not proof, but it's an unsettling probability to consider. And here where the idea turns inward. Even if we set aside alien programmers and cosmic computers, The reality you experience is still, in a sense, a simulation, one generated by your brain. Your senses take in fragments of the world, your brain predicts and fills in the rest, and the result is the seamless movie you call reality. It's convincing because it's designed to be convincing. That doesn't make it fake, but it does make it curated. Dreams are the clearest reminder of this. In dreams, your brain spins entire worlds without any external input. You feel the texture of a wall, smell the rain on the street, hear voices and music, all of it conjured from memory and imagination. If you've ever had a lucid dream, you know how easily your mind can accept the impossible as normal until some small inconsistency tips you off. The waking world might be more consistent, but how sure are you that it's fundamentally different? Some physicists and philosophers take a softer approach to the none of it's real idea. They propose that what we think of as reality is a kind of emergent phenomenon, a high-level pattern that arises from something more fundamental, the way a rainbow arises from sunlight and water droplets. You can measure a rainbow, predict where it will appear, photograph it, even walk toward it, but you can never touch it because it isn't an object. It's a relationship between light, water, and the observer's eyes. If matter is like that, if it's an emergent pattern in some deeper, invisible framework, then asking whether it's real is like asking whether a rainbow is real. The answer depends on what you mean by real. This uncertainty doesn't have to be frightening. In fact, it can be strangely liberating. If the world is in some sense a construction, then so are the limits you think are built into it. If space and time are flexible, if particles can be in multiple states, if reality can shift depending on how it's observed, then why should you assume that the rules of your life are fixed and unchangeable? Of course, there's a danger in leaning too far into the idea that nothing is real. Take it too literally, and you might be tempted to dismiss the consequences of your actions, to retreat into a kind of philosophical solipsism where nothing matters. But that misses the point. Even in a simulation, even in a dream, the experiences you have are real to you. Pain still hurts, joy still uplifts, love still transforms. The meaning you create doesn't depend on whether the universe is running on silicon, neurons, or something we haven't imagined yet. And here's the strange thing. If we ever did find proof that we live in a simulation, it might not change the day-to-day reality of our lives at all. You'd still need to eat, sleep, love, and dream. The rain would still fall. Music would still move you. The knowledge would be staggering, yes, but the lived texture of existence would remain. Perhaps that's the secret comfort in asking whether any of this is real. The question stretches your imagination, forces you to step outside the familiar frame. But the answer, whatever it is, doesn't erase the beauty of the frame itself. Whether the stars are nuclear furnaces or pixels on some cosmic screen, they are still beautiful. Whether the touch of a friend's hand is electromagnetic repulsion between atoms or a programmed sensation, it is still connection. So maybe the question isn't, is it real? Maybe it's, what will I do with it, real or not? Because in the end, whether we are atoms in a vast universe or lines of code in an elegant simulation, the experience of being here now is the one reality we can't deny. And if none of it is real in the way we once thought, that just means we've been invited into a deeper mystery, one where the boundaries between real and unreal are as fluid as the boundary between particle and wave, matter and energy, self and universe. There's a quiet moment after you've turned over all the theories and possibilities when you have to admit something to yourself. No matter how far we've come, we still don't really know what's going on. Not fully, not deeply enough. For every piece of the puzzle we've put in place, there's an empty space waiting beside it, a shape we can't quite fill. And maybe that's the most honest thing we can say about reality. It's still, and perhaps will always be, unfinished. Science, for all its rigor, thrives on these gaps. In fact, the gaps are the engine that drives it. Every mystery is an invitation to look again, to build better tools, to imagine beyond what's currently possible. But some mysteries feel different, heavier, stranger. These are the ones that don't just resist answers, they seem to question the very frame we're using to ask them. Take dark matter. We know it's there because of how it tugs on galaxies, because of the gravitational fingerprint it leaves in the cosmic web. But we can't see it, touch it, or make it in a lab. Decades of experiments have searched for the particles that might make it up, with nothing to show but increasingly sensitive detectors recording increasingly subtle silences. Is dark matter some undiscovered particle, a shadow form of gravity, or does it mean our entire theory of gravity needs rewriting? We don't know. Or dark energy, even stranger. Not only is the universe expanding, it's accelerating in its expansion. Something, somehow, is pushing it apart faster and faster. We've given that something a name, dark energy, but the name is just a placeholder, a neat label for something we don't understand at all. It could be a property of space itself. It could be a field that permeates everything. It could be, well, almost anything. Even the things we think we do understand are, upon inspection, surprisingly slippery. We can write equations that predict how particles interact to absurd precision, but what those equations mean, what they say about the actual nature of reality, is still open to interpretation. Quantum mechanics works flawlessly in practice, but no one agrees on the correct philosophical interpretation of what it describes. Is the wave function a real thing, or just a tool for calculating probabilities? Does it collapse when we observe, or is collapse an illusion? Do all possible outcomes happen in parallel universes? Zoom in on the smallest scales, and you find the Planck length a size so small that our current theories simply stop making sense. Below this length, quantum mechanics and general relativity, our two best theories, start contradicting each other. To resolve this, physicists search for a theory of quantum gravity, a unification of the cosmic and the microscopic. But the math is fierce, the experiments nearly impossible. String theory offers one path, loop quantum gravity another, but both are far from confirmed. Zoom out to the largest scales and you find another mystery. Why does the universe look so smooth? The cosmic microwave background, the faint afterglow of the Big Bang, is almost uniform in every direction, yet galaxies and clusters have formed. Inflation theory tries to explain this by proposing that the universe expanded faster than light in its first moments, smoothing everything out. But inflation itself raises new questions. What caused it? Why did it stop? Could it happen again? Then there's the deep riddle of time. We experience it as a one-way flow from past to future, but the fundamental laws of physics don't require this arrow. They work just as well backward as forward. So why does time feel like it moves? Why can you remember yesterday but not tomorrow? Is the flow of time an illusion, like solidity, a construct of consciousness rather than a property of the universe? And beneath all these questions lies perhaps the deepest one of all. Why is there something rather than nothing? Even if we someday write down the perfect equation that explains how the universe works, that equation will still be haunted by the question of why it exists at all. Why should there be laws, particles, fields, or space-time itself? Why not nothing? And if nothing is unstable, always bubbling into something, why should that be true? In the face of such questions, there's a temptation to retreat, to close the book and say, well, we can't know, so why ask? But mystery isn't a flaw in the story. It is the story. The unknown is not a gap we must fill as quickly as possible. It is a space where wonder lives. Think about how many times in history humans have stood on the edge of the known and assumed that was the limit. Before Galileo turned his telescope to the sky, the moon was a perfect, smooth sphere. Before microscopes, a drop of pond water was empty. Before modern physics, atoms were indivisible, space was static, and time was absolute. Each time we thought we were nearly done, and each time the universe pulled a new layer away, revealing a stranger, deeper reality. This is why scientists can seem almost reverent when they talk about not knowing. The mysteries aren't frustrating intrusions into an otherwise tidy picture. They are signs that the picture is still alive, still unfolding. If we ever did know everything, the universe would become static, inert. The questions are what keep it moving. And maybe this isn't just about physics. Mystery runs through our own lives in the same way. You don't really know what another person is thinking, no matter how well you know them. You don't know what will happen next week, or even in the next hour. You can't predict what moment will change you, or what word will linger in your mind for years. Life's uncertainties are just the human-scale reflection of the universe's uncertainties, reminders that we live not in a fixed story, but in one that's still being written. Some traditions, spiritual and philosophical, go further. They suggest that mystery is not a flaw in perception, but a deliberate part of reality, that if we could see the whole truth at once, we would lose something essential. That uncertainty is what makes curiosity possible, and curiosity is what makes consciousness meaningful. If the universe is a kind of conversation, mystery is the pause that invites a reply. So maybe we don't have to rush to solve every paradox. Maybe we can let some of them remain open, not because we've given up, but because we understand that the unknown has its own kind of value. Just as silence makes music richer, the unanswered makes knowledge more alive. And there's one more twist to this. Some of the mysteries may never be solvable from within the universe. Just as a book's characters can't read the manuscript from the outside, we might be bound by the rules of the very reality we're trying to explain. That doesn't mean the answers aren't there, only that they might be forever beyond our reach, which is its own kind of poetry. Even if we never grasp the ultimate truth, we can still live fully inside the mystery. We can still marvel at the night sky, still follow the equations to their strange conclusions, still feel the wonder that comes from knowing that we do not and cannot know it all. That wonder is not a consolation prize, it's the whole point. Because in the end, whether the universe is made of particles, fields, code, or something entirely beyond our comprehension, the fact that it leaves room for questions might be its greatest gift. The missing pieces are not flaws, they are invitations. And every time you feel that tug of curiosity, every time you sense that the world is bigger than your understanding, you are touching the same mystery that has pulled at human minds for thousands of years. It is not an absence, it is a presence. It is the hum under the silence, the space between the stars, the unlit room that waits for you to open the door. And maybe, just maybe, we are meant to keep some doors closed, not to avoid what's behind them, but to savor the moment before we find out. For all the vastness and quantum weirdness, you still wake up every morning in a body. You stretch, you breathe, you feel the sheets against your skin. Whatever the universe is made of, however deep its mysteries run, your first experience of it each day comes through the warm, grounding familiarity of yourself. And it's easy to forget that the same mind-bending physics shaping galaxies is at work inside you, that your body is not just living in the universe, but is the universe in one of its rarest and most complex arrangements. Think of your breath. The air you draw in carries oxygen atoms forged in the heart of stars billions of years ago. Those atoms find their way into your blood, where iron atoms, also born in stellar explosions, bind to them in a dance that repeats itself thousands of times each second. The carbon dioxide you exhale will drift into the air, perhaps to be drawn in by a tree, where it will be broken apart and reassembled into sugars. From the cosmic scale to the cellular scale, matter is in constant conversation. And yet, your body's experience of this exchange isn't one of physics equations or atomic structures. You don't feel oxygen molecules binding to hemoglobin. You feel the relief of a deep inhale after holding your breath. You feel the ease that comes with exhaling. The brain translates atomic interactions into sensations, giving you a human-scale language for processes that are, at their core, quantum events. The same is true for touch. That hug from someone you love, it's a cascade of electromagnetic repulsions between your atoms and theirs, translated into a warmth that can calm your heartbeat. Your skin is covered in receptors tuned to pressure, texture, and temperature, and each one is sending a steady stream of electrical signals to your brain. But the brain doesn't present them to you as data. It blends them into the single, cohesive feeling of contact. Even your sense of self, that feeling of being a continuous, you moving through time, is woven from these sensory translations. Your cells are constantly dying and being replaced. The matter in your body today is not the matter that was here 5 or 10 years ago. You are a shifting arrangement of particles, bound together temporarily, like a wave cresting in the ocean. And yet, because your brain maintains a continuous narrative, you feel stable, consistent, solid. Circadian rhythms, your body's daily cycles, are another example of your private connection to the universe's deeper structure. Inside your brain, in the suprachiasmatic nucleus, a cluster of neurons keeps time using chemical signals and gene expression patterns. These rhythms are synced to the day-night cycle of the Earth, which is itself a product of the planet's rotation, a cosmic movement that began billions of years before humans existed. Without realizing it, your body is keeping time with the turning of the Earth, adjusting everything from hormone levels to body temperature in response to light and darkness. Sleep, too, is a frontier where the vast meets the personal. When you drift off, your brain moves through cycles of electrical activity that scientists can measure but still don't fully understand. In deep sleep, your body repairs tissue, strengthens immune responses, and consolidates memories, processes that depend on molecular interactions at the smallest scale. In dreaming sleep, your mind creates worlds as vivid as waking reality, worlds that can be influenced by your emotions, your memories, and perhaps even the sensory inputs around you. The boundary between real and imagined blurs every night. Your heartbeat is another private interface with the laws of physics. At the simplest level, it's a pump moving blood through a network of vessels, but the way it does this depends on the precise timing of electrical impulses, the chemical composition of your blood, and the shape of proteins that themselves are folded according to the quantum mechanical rules of chemistry. The regular thump in your chest is a macroscopic rhythm emerging from microscopic order. Even your thoughts are built from physical events. Every idea, every memory, every flash of emotion is carried on electrochemical signals passing between neurons. Those signals are triggered by ion channels opening and closing in cell membranes, events governed by the same physical laws that describe the flow of electrons in a wire or the binding of atoms in a molecule. Consciousness, that intimate and ineffable experience of being you, is inseparable from the physics of your body. And yet, because the brain's job is to give you a coherent and actionable version of reality, you rarely feel any of this in its raw form. You don't feel the constant exchange of matter and energy between your body and the world. You don't feel the quantum probabilities of the electrons in your cells. You feel hunger or thirst or the comfort of a warm blanket. The deeper mechanics are hidden, and perhaps they have to be. There's a quiet irony here. We often think of science as something out there, a way of studying nature in distant stars or in particle accelerators. But some of the deepest and most profound physics is happening inside you right now, in the heat of your metabolism, in the firing of your neurons, in the way your body maintains its delicate balance despite constant change. If you start to pay attention, you can feel the rhythms of this balance, the way your body temperature dips at night, the way your pulse quickens when you're startled, the subtle heaviness in your limbs after a long day. These sensations are not random. They are your direct experience of the same forces and processes that shape the universe at every scale. And perhaps this is where the mystery becomes personal. It's one thing to marvel at the emptiness inside an atom or the expanse between galaxies. It's another to realize that your very sense of self is built on patterns that are temporary, emergent, and deeply entangled with the environment. You are not separate from the universe. You are a local expression of it. Every breath, every beat of your heart, every fleeting thought is part of a chain of events stretching back to the beginning of time. This is why the most profound encounters with reality often feel both humbling and empowering. Humbling because you see how small you are in the vastness, how brief your life is in the timeline of the cosmos. Empowering because you realize that you are not apart from that vastness. You are made of it, shaped by it, moving with it. Even the most ordinary moments, washing your hands, drinking water, looking into someone's eyes, are shot through with this connection. The atoms in your body were once part of other people, other creatures, other worlds. The calcium in your bones might have been part of an ancient seashell. The hydrogen in your cells has been here since the dawn of the universe. When you stand outside at night and feel the wind on your skin, you are literally touching matter that has traveled across space and time to meet you. In that sense, your body is not just living in the universe. It is a bridge between the smallest scales and the largest. The quantum fluctuations that shaped the early cosmos still ripple through you. The same gravity that binds galaxies together keeps you tethered to the Earth. The same electromagnetic forces that hold electrons in orbit around nuclei let you hold a pen or type these words or touch someone's hand. And while we often think of our relationship to the cosmos in abstract, poetic terms, your body lives that relationship every second. It doesn't need to know the equations. It doesn't need to prove the theories. It simply does what life has always done. It keeps time with the turning Earth, exchanges matter with the environment, and sustains itself within a reality that is both impossibly strange and utterly familiar. Long before anyone spoke of atoms or quantum fields or the bending of space-time, there was the sky. That's where the human story of understanding begins, not in laboratories or textbooks, but in the act of looking up. Our earliest ancestors saw the sun rise and set, the moon wax and wane, the stars wheel overhead. They saw patterns and they told stories about them. The bear in the stars, the hunter, the serpent, the cosmic river. For most of human history, the world was explained in terms of myth. The earth might rest on the back of a turtle or be held up by a great tree. The sun might be a god's chariot, the stars his campfires. Matter wasn't an abstract concept. It was earth, air, fire, and water, each with its own personality, its own moods. Thunder was a voice. Wind was a spirit. This wasn't ignorance. It was a kind of poetry, an attempt to weave the unknown into something human-shaped. But even in those ancient stories, you can feel the first stirrings of scientific thinking. Farmers noticed that the seasons followed the sun's path and began to measure its movement with stones or wooden posts. Sailors mapped the stars to guide them across oceans. Healers learned that certain plants relieved pain, others closed wounds, and they kept track of those patterns. Curiosity was already there, it just wore the clothes of story. In ancient Greece, curiosity began to push further. Philosophers like Thales and Anaximander started asking what the world was made of. They wanted a single underlying principle, something universal. For Thales, it was water. For Anaximenes, it then came Democritus, who proposed that everything was made of indivisible units, atomos, too small to see, uncuttable, and eternal. It was a bold guess, with no way to prove it, but it planted a seed that would lie dormant for centuries. Meanwhile, in India, thinkers of the Vedic and later Buddhist traditions were also exploring the nature of reality. Some described matter and consciousness as interdependent, others as illusions woven from impermanent patterns. In China, Taoist and later Neo-Confucian thinkers saw the world as a balance of forces, yin and yang, flowing through all things. These were different lenses, but all were asking the same fundamental question: what is this? The medieval period, at least in Europe, is often portrayed as a pause in progress, but that's misleading. In the Islamic world, scholars like Alhazen and Avicenna were refining optics, medicine, and chemistry. In China, Shen Qiu wrote about magnetic compasses and geological change. Knowledge was being preserved, tested, and expanded, even if the tools were still limited. Then came the scientific revolution, and with it, the first real instruments to extend human senses. Galileo turned his telescope to the heavens and saw mountains on the moon, moons around Jupiter, and the phases of Venus, all of which hinted that Earth was not the center of everything. Robert Hooke peered through a microscope and revealed that living things were made of tiny, intricate structures. Newton tied it together with his laws of motion and gravity, showing that the same rules applied to falling apples and orbiting planets. It was a heady time. The universe seemed finally within our grasp, its workings transparent to human reason. The old myths were giving way to a new one, the myth of total knowability. But this new myth was not without its blind spots. Matter was still imagined as tiny, solid billiard balls. Space was an unchanging stage. Time ticked forward like a metronome. The human senses, extended by instruments, seemed capable of capturing everything that mattered. The 19th century brought chemistry into its modern form. Dmitri Mendeleev arranged the known elements into the periodic table, leaving spaces for those yet to be discovered. The atom became not just a philosophical idea, but a practical one, something you could calculate, something you could measure indirectly by its effects. Then, at the turn of the 20th century, the old picture began to crumble. Rutherford's gold foil experiment revealed the empty space within the atom. Planck's quantum hypothesis, Einstein's relativity, Bohr's model of the hydrogen atom, each was a crack in the Newtonian wall. The deeper scientists looked, the stranger things became. The quantum revolution of the early 20th century rewrote the rules entirely. No longer were particles tiny marbles, they were probability waves. No longer was space a rigid stage, it could bend and stretch. Time itself could run at different rates, depending on speed and gravity. Even mass and energy turned out to be interchangeable, bound by the famous equation E equals mc2. These discoveries didn't arrive in a smooth line. They came in bursts, often resisted at first, debated fiercely, tested in painstaking experiments. Each breakthrough brought more questions than it answered. The neat, clockwork universe had been replaced with one that was dynamic, probabilistic, and deeply interconnected. And yet human understanding didn't stop at the shock of the quantum and the cosmic. Technology leapt forward: particle accelerators, space telescopes, genetic sequencing machines. We began mapping the cosmic microwave background, the faint afterglow of the Big Bang. We detected gravitational waves rippling through space-time. We photographed the shadow of a black hole. The more we learned, the more the old boundaries blurred. Biology began to merge with physics and chemistry. Information theory began to influence cosmology. Some scientists began to talk about the universe as a computation, others as a hologram, still others as a multiverse of infinite possibilities. But the story of understanding is not just a story of accumulation, it's also one of humility. Every time we think we're close to the final theory, the universe reveals a deeper layer, a more subtle pattern, a more baffling mystery. The history of science is, in that sense, a long lesson in being wrong and in letting go of the comfort of certainty. What's remarkable is how this history mirrors an individual's journey. As children, we often believe in simple, absolute truths, that adults know everything, that the world is solid and safe. As we grow, we discover complexity, contradiction, and ambiguity. Our view of reality expands, and we must decide whether to cling to old certainties or embrace the open-endedness. Humanity has been making that decision over and over for thousands of years. The truth is, our story of understanding is far from over. In some ways, it may be just beginning. We are only a few centuries into the scientific method, a blink in cosmic time. Our instruments, powerful as they are, can only probe a fraction of the scales that exist. There may be realms of reality so far beyond our current reach that we can't yet imagine the questions, let alone the answers. And yet there's something beautiful in knowing that our understanding is provisional, that every model we build is just a stepping stone. The myths of the past were not failures, they were the best maps available at the time. Our current theories are the same, temporary, useful, and destined to be replaced. The map is not the territory. If you could lay the entire human story of understanding side by side, from the first myths told around firelight to the latest results from the Large Hadron Collider, you'd see a single thread: the drive to make sense of where we are, what we are, and why there is anything at all. That drive has outlived empires, crossed oceans, and bridged languages. It is as much a part of us as the breath in our lungs. And perhaps that's the most enduring truth of all. We are not just made of the universe, we are curiosity about the universe. We carry forward the questions of those who came before, and we hand them, unfinished, to those who will come after. The story is unending because the storyteller, reality itself, never stops speaking. After all the centuries of looking, measuring, building models, and peering deeper, a strange possibility begins to whisper from the edges of our understanding. What if the thing we've been trying to describe this whole time isn't actually there in the way we imagine? This is not the same as saying nothing exists. You still feel the ground under your feet. You still watch the sun rise, hear the sound of rain, taste food, and feel warmth on your skin. Experience itself is undeniable, but the interpretation of what lies beneath those experiences, the assumption that there is a fixed, independent thing called matter, that's what may be in question. Physics has already forced us to surrender the idea of solidity. Atoms are mostly empty space, their substance, consisting of energy and probability patterns. Zoom in further, and even particles aren't stable objects. They are excitations of fields, temporary disturbances in something more fundamental. They blink into and out of existence, borrowing energy from the vacuum and repaying it almost instantly. Some interpretations of quantum mechanics go further still, suggesting that what we call objects are just convenient fictions, stable patterns in the data our senses and instruments provide. The equations describe relationships, not things. What we perceive as a table may be less a chunk of matter and more a persistent set of interactions, like a whirlpool in a river. The whirlpool appears solid, but there's nothing in it except the movement of water. This idea isn't new. In Buddhist philosophy, the concept of sunyata, often translated as emptiness, holds that all things are empty of inherent existence. They arise from causes and conditions, depend on other things to be what they are, and change constantly. What we call a thing is really just a temporary arrangement, a momentary knot in the fabric of conditions. Modern physics echoes this, though in different language. The standard model of particle physics doesn't give us billiard balls. It gives us a web of fields whose excitations interact according to probabilities. And even those fields may not be fundamental, they could be emergent from something deeper still, something we don't yet have the tools to describe. This is where some physicists talk about spacetime and matter as emergent phenomena. Just as temperature emerges from the collective motion of molecules, space and time might emerge from something more primitive, perhaps quantum entanglement patterns, perhaps pure information. In such a view, the universe is not built from stuff, but from relationships and correlations. If that's true, then asking, what is matter really, might be like asking, what is a wave really? You can describe a wave in terms of height, frequency, and speed, but there is no thing called wave apart from the water or air or medium moving in a certain way. Matter too might be nothing more than a pattern, an appearance that arises when certain conditions are met. There's an unsettling consequence to this. If matter is not fundamental, then much of what we take as the real world may be just the surface of a much deeper, stranger reality. All of our senses, all of our measurements, may be interacting only with the interface, the user-friendly dashboard, not with the operating system itself. Think about your phone or computer screen. You see folders, icons, and buttons. You click on an icon and something happens, but there's no actual folder inside the device. The folder is a visual metaphor for stored data. The real activity is happening in patterns of electrical charges inside circuits, far removed from the image you interact with. The interface is not a lie. It's a functional representation designed to let you navigate without knowing the underlying complexity. Some cognitive scientists, like Donald Hoffman, argue that our perception works the same way. Evolution didn't shape our senses to see reality as it is. It shaped them to present a simplified interface that maximizes survival. Color, shape, solidity, these may be as much symbolic shortcuts as your desktop icons are. They hide the complexity because seeing it wouldn't help you stay alive. If we take that seriously, then what we call the physical world might be more like a virtual reality interface, consistent, functional, shared between observers, but not the underlying truth. The fact that it works doesn't prove it's the whole story. And maybe this explains why every time we dig deeper, reality seems to dissolve into something more abstract. Molecules become atoms, atoms become subatomic particles, particles become quantum fields, and fields may be expressions of pure mathematical structure or information. The more we zoom in, the more the thingness evaporates. This isn't to say the interface isn't worth studying, quite the opposite. Just as understanding your computer interface helps you use it better, understanding our perceived reality helps us navigate it, build technology, and improve life. But if you mistake the interface for the whole machine, you limit what questions you can ask. And here's the strange comfort. Even if matter, space, and time are not fundamental, that doesn't make your life less meaningful. The warmth of sunlight on your skin, the sound of a friend's laughter, the quiet peace of a night sky, these experiences are real in the only way that matters to you. They are the content of the interface, and meaning lives in content. If the table you write on is an emergent pattern, you can still lean on it. If your body is a whirlpool in a river of quantum fields, you can still breathe, eat, and love. The unreality of matter doesn't dissolve the reality of living. And perhaps it's not even right to call it unreal. Patterns are real, relationships are real, waves, rainbows, and dreams are real in their own ways. Maybe the mistake was ever thinking that real had to mean fundamental in the first place. It's possible that reality is layered, with each layer emerging from the one below it, each having its own kind of truth. Your sensory world is real for you. The molecular world is real for chemistry. The quantum field is real for physics. Each truth works at its own scale, and each truth dissolves if you push it too far into another's domain. So maybe the question isn't, is matter real? Maybe it's, at what level and for what purpose? Your body is real enough to live in. Your emotions are real enough to guide your choices. The atoms making you up are real enough to obey the laws of physics. Whether there's something more fundamental beneath it all is a question we may never stop asking. And in a way, that's the beauty of it. Reality, whatever it is, keeps receding as we approach. Like a horizon, it's always just beyond reach. Every answer opens into another question, every certainty softens into possibility. The chase is endless, and maybe that's the point. And now, after wandering through atoms and galaxies, equations and mysteries, we are back here in this single moment. You listening, breathing, the world around you holding steady, as if none of the strangeness we've explored has touched it. The chair beneath you feels solid. The air feels still. Somewhere nearby, a clock ticks, or maybe there's the faint hum of a fridge or the rush of distant traffic. The small, ordinary details return, carrying with them the gentle gravity of home. Strange truth is, nothing has changed, and yet everything has. The table is still a table, your hands still your hands, but now you know what they are made of, not just wood, not just flesh, but vast stretches of empty space stitched together by invisible forces. Now you know the atoms that make you are older than the earth, forged in stars and scattered through cosmic storms before drifting here to become the body you live in. You are not separate from the universe's story, you are its latest chapter. It's tempting to let these realizations overwhelm you, to feel small against the scale of galaxies or lost in the uncertainty of quantum probabilities. But maybe small isn't the right word. You are local, yes, a particular arrangement of matter and energy in a particular corner of space and time. But you are also connected through gravity, through light, through the slow cycling of atoms, to everything that ever was and ever will be. When you look at your hand, you are seeing not just skin and muscle, but the work of billions of years. Hydrogen from the early universe, carbon assembled in ancient forests, water that once rained on mountains you'll never visit. The same iron in your blood may have flowed in the blood of other creatures millions of years ago. In this way, nothing you are is entirely yours, and yet nothing you are exists without you. Even the act of noticing this, the awareness itself, is extraordinary. A cluster of particles in the vast, dark universe has arranged itself so intricately that it can look back on the universe and wonder what it's made of. You are that arrangement. You are the question and the questioner, the observer and the observed. We've talked about how matter is mostly empty space, about how the solidity you feel is an electromagnetic standoff, about how particles behave like waves until measured, about the possibility that everything is an interface, a rendering, a pattern in some deeper code. And yet, despite all that, life goes on exactly as it did before you knew it. The spoon still stirs your tea, the bed still holds you at night, the sun still rises. Knowing the trick doesn't make the magic disappear. This is one of the quiet paradoxes of life. Understanding the illusion doesn't strip it of meaning. If anything, it can make it richer. When you know that the chair you sit on is a field of energy interactions, the fact that it can hold you becomes even more miraculous. When you know that the breath you take in is made of atoms born in distant stars, the simple act of breathing becomes an act of communion with the cosmos. And maybe this is the point of all the wondering, all the theories, all the nights spent staring at the sky. Not to replace the world with an abstract diagram, but to see more of it, to see the unseen layers that make the everyday glow a little brighter. Science doesn't steal the poetry of reality, it writes new verses for it. So here you are, at the end of a long journey that was never really about reaching a conclusion. Because reality, whatever it is, doesn't seem to have a final page. The deeper you go, the more the story opens. The more you learn, the more you realize how much you don't know. And if you can make peace with that, if you can let the unknown be part of the beauty, then the mystery becomes a companion rather than a problem to solve. This is why, after all the facts and theories, we return to the simplest things: the feel of your body resting, the rhythm of your breath, the awareness of being here. The universe is not just something out there to be studied. It is also this: your heartbeat, your thoughts, the light in the room, the silence between sounds. You are living inside it, and it is living through you. Think about that for a moment. You are the universe noticing itself. You are a way for stardust to wonder about stardust, for matter to reflect on the fact that it exists at all. And whether the foundation of reality is particles, waves, fields, information, or something beyond all of that, it has, for a brief stretch of time, taken the shape of you. And right now, in this quiet moment, the vastness doesn't need to feel distant or cold. It can feel close, warm, almost familiar, because you are made of it. The atoms in your body have been part of countless other forms before you, and will be part of countless others after you. You are part of an endless cycle, and for now, you get to experience it from the inside. So let this thought settle in you. The mystery is not somewhere far away, waiting to be found. It is here, in the texture of your skin, in the air you breathe, in the flicker of your mind. You are already inside it. You always have been. And whatever this thing called reality turns out to be, it is holding you right now, just as you are holding it, in your attention, in your awareness, in your willingness to wonder. The night will come, you'll close your eyes. And maybe, as you drift into sleep, the boundaries between you and the rest of it will soften, as they always do, until you are simply part of the quiet hum of existence again. And when you wake tomorrow, or in some other moment far from now, the story will still be here, waiting. Not because it needs an ending, but because it doesn't have one. So breathe, let the strangeness and the familiarity blend together. Let the questions rest for now. And remember, in this moment you are here, you are alive, you are the universe dreaming itself awake.